thank you for the introduction, Alberto. I'm starting again, and to the organizers for the opportunity to speak to you. So what I want to do is talk about something that came up when I was looking at complex manifolds with conical singularities. There is a very interesting thing that happens on the boundary of such a thing. The boundary is what happens when you blow up the conical singularities, and then you end up with a manifold with boundary. And then on the boundary, you get a kind of structure, which is not a sphere structure, but it's related to a sphere structure in some sense. And so this led me to actually look into it more carefully, and I found it interesting. So talking about this, which is not something that I did very recently, but nevertheless. So what I will do is what we will be dealing with is compact manifold M connected in a boundary together with a non-vanishing real vector field that is a Killing vector field for some Riemannian metric. And I don't care what the Riemannian metric is, only that there is such a Riemannian metric. And my point is that it behaves in a lot of ways, like that such a thing, or M together with the vector field, behaves in a lot of ways as a circuit bundle over a compact base. So this is one example of one illustration of this point, which is a situation in which one has a differential operator acting on sections of a bundle, and the operator actually commutes with the vector field L, with the vector field T, and some sort of in the boundary permission, and then you have an environmental measure and so on. The operator is assumed to be normal. And then what happens is that if you look at the kernel of T,
sorry, Gerardo, I cannot hear you very well. So can you maybe speak closer to the microphone? Oh, sorry.
Okay, 1 second. Okay, can you hear me better now?
Yeah, much better.
Yeah, okay. Okay, so what happens is that when you look at the kernel of the operator, so the kernel of the operator is invariant under the operator L because it's a commutation thing. And so you can look at the kernel inside L2, which is a Hilbert space, and then regard LT, the restriction of LT to this as an unbounded operator, and then look at its maximal ideal, and at its maximal domain, and then what you get is a Fredholm self-adjoint operator with a compact parametrics. Okay, this is under some hypothesis that we'll study more carefully later. Okay, and then the application is that somehow this is related. So hypolepticity in this case, I will tell you exactly in what sense. One gets a theorem which is similar to a Kodaira vanishing theorem. And then I will tell you what the proofs are. There's a bit about the proofs. So the setup is, again, we have a closed manifold, which is compact, no boundary, connected, a nowhere vanishing vector field that preserves some metric. We have the flow of the vector field and an invariant density, a Hermitian bundle with metric H, and then a unitary operator on the bundle that covers the action of the vector field T. And then one has a Lie derivative defined with these ingredients, which is that if you take a section of maybe I can point, yes. You take a section, so you have a point on the manifold, and then you move forward by a certain amount, A sub T. You look at the value of the section there, and then you bring it back using the other action, the action on the vector bundle. And then you get a function of the real variable T that you can then differentiate. And then that's the operator L sub T, which is it's exactly the same as a Lie derivative. And in fact, in the application, it is a Lie derivative. It's the Lie derivative of some sort of forms. So the other ingredient is you have a differential operator of order M It commutes, as I said before, and is formally normal. And then the ellipticity condition that I said, or that I need, is that you look at the principal symbol of P plus the principal symbol of minus ILT to the power M, which is the order of the operator, minus lambda times I has to be invertible when lambda is in capital lambda, which is a real line inside the complex space. And then the result, in particular, when lambda is equal to 0, what we get is the invertibility of the sum of this, what you get is the invertibility of this operator, P plus minus I L T to the M. And then you take us, so H is what? H is the kernel of P intersected with L2, which is a Hilbert space. You let D be the maximal domain of L sub T. So this condition is you have an element in L2, which is killed by P. You apply LT to that. You want it to be in L2 also. Once it is in L2, it's also in H automatically because of the commutativity. You get an operator like that, and then the statement is that this operator is self-adjoint with compact resolvent, in particular Fredholm. Okay, so what has this to do with the circle bundles? Okay, so in this, still in the general situation, suppose that you have a point in M, you have the orbit through the point, and then you define a relation of equivalence, which is P equivalent to P prime if and only if P prime belongs to the orbit, to the closure of the orbit through P, the orbit of A sub T through P. This is one place where one uses that LT preserves a metric, because this actually gives that this is a relation of equivalence. If you don't assume that, then you cannot prove that this is a relation of equivalence, because you can give counterexamples. The symmetry gets lost. So take now the projection, and then one can show that the fibers of these projections is a torus. They are tori. The tori, they can vary dimension. They're not tori of the same dimension. Let's keep this. And one can actually show, just because one can show it, that there is a part of M that I call the regular part of M, and there is a part of the base of the quotient that I can call the regular part, so that the projection, I should have used the other P, not pi, is a principal torus bundle. Okay. So in some sense, this resembles a circle bundle, because what it is a principal bundle over a group that is actually abelian. Okay, so the circle group is abelian, the torus group is abelian. So this is it's in this sense that it resembles a circle bundle, and then from the commutativity of the group, one gets a lot of properties that actually give you this resemblance with circle bundles. For instance, I can prove something which is like a classification theorem that is similar to Chern classes. Okay, things of that sort. As an example, so now a concrete example. So suppose that you have a compact complex manifold, and M is the circle bundle of a holomorphic line bundle. So M is the set of points. So the line bundle has a Hermitian form. I give it a Hermitian form. I look at the unit circles, and then I get a manifold a submanifold of the ambient manifold L. Okay. I can make T be the generator of the action of multiplication by e to the IT. So this is multiplication in the fiber, in the circle variable. Okay. So that would be the vector field. Then, because this is a hypersurface in the complex manifold L, one has a CR structure inside M, a CR structure in M, and then one can look at the Kohn Laplacians on Q forms. So this is 0Q forms on M. Okay, and that would be the operator, and then it commutes automatically. It will commute. This is elliptic. This is actually a positive operator. So the business about invertibility when you have the lambda in there, lambda I, it's going to be satisfied when the line lambda doesn't coincide with the real axis in the complex plane. So this, I'm referring to this property here. Oops. Anyway, that property. Okay, so this property is satisfied, and then one has the conclusion. And then what's the point? The point is that there is an isomorphism. On the other hand, there is an isomorphism. So one has, by the theorem, one has eigenspaces. One has this, the composition of the kernel of P. So what is the kernel of P? The kernel of P is actually isomorphic to the on the one hand, it's isomorphic to the CR cohomology in degree Q, but that's the same thing as for a given value of M. So this decomposition into eigenspaces is actually, each of these spaces is isomorphic to the space of holomorphic sections of the tensor power of L with itself M times. If M is negative, it's tensor power with the dual. Okay, so these spaces which are the eigenspaces for the vector field for this operator here, the eigenspaces for this, they are actually in one-to-one correspondence with the cohomology groups downstairs. And then if you can prove that there's no spectrum, for instance, for M positive, then what one is proving is a vanishing theorem. Okay, that there are no sections of this when M is negative. That the space of sections of this is zero, that this space is zero when M is negative. Okay, so this is the connection with vanishing theorems. Okay, so how does the ellipticity come in? Going back to the general situation. Okay, so the principal symbol of this operator is actually a scalar times the identity, and this is easy to see. You just take a section, multiply by e to the ISF. F is a real value function. Do the operator, multiply by this, divide by S, take the limit, and what you get is this expression. Okay, so this derivative, it will differentiate F, and then you get an S, that S cancelled by this. Otherwise, you get it here, but then in the limit you get zero, so you get this. Okay, so this is a scalar thing. This is a scalar operator, and then because of the invertibility of this operator, one knows that on the characteristic variety of P, tau, this function tau is not zero. So the characteristic variety splits into, because if suppose that you are at a point of the characteristic variety, at that point, this is not invertible. The symbol of P is not invertible by definition. And suppose that at that point, tau is equal to zero, then what you get is just the principal symbol of P. That's what this expression becomes. And then it's not invertible, okay? So you don't have ellipticity there. Okay? So the characteristic variety then splits into a positive part, a part where tau is positive, and a part where tau is negative. And then what one can prove is that if P is hypoelliptic on the, let's say, positive side, then the spectrum of this guy lies mostly on the negative side. Okay, the operator becomes semi-bounded from above. Okay. So this is the kind of vanishing theorem that one gets. If M carries an invariant, so for example, if M carries an invariant Levy non-Dirichlet structure, then the cone Laplacians are apoelliptic. This is a theorem that is known. Then the cone Laplacians are apoelliptic in degrees that are different from plus or minus q, which is the positive or negative the number of positive or negative eigenvalues of the Levy form. And the hypoellipticity is known by work of Melt and Shostak independently in the 70s, but one can also from, because this is microlocal stuff, okay, but this is also goes back to work of Kohn in the 60s. Okay, so you get finite in degrees where the operator is apoelliptic, you just get finite spectrum, because then on the positive side, you have at most finitely many eigenvalues, and on the negative side, you only have at most finitely negative eigenvalues, so you only have finite spectrum. Okay. if you apply this in the example of the line bundle, okay, what this says, it's not as strong as Kodaira's theorem, because it doesn't say that the cohomology groups, which are the ones down here, are 0 in those degrees. It only says that they are finite dimension. That only for finitely many m's will, no, m is the eigenvalues. For finitely many m's will you get a non-zero space. Okay, Kodaira says there are no, all of them are 0. The proofs, okay, so I think I'm going to probably very fast. So what are the proofs? Okay, so suppose suppose that Q parametrics is a T-invariant parametric for this operator. So this operator is elliptic. And the condition on the invertibility of this expression for lambda on this line, which gives ellipticity, it also gives more. It gives that this line is actually an array of minimal growth. So in fact, this operator has non-empty resolvent. Okay, so if necessary, I can work with the resolvent, but this also tells me that this operator has index 0. So I can build Q out of looking at the restriction of P to the orthogonal of the kernel, say what is the inverse there by hand. Okay, then I get an error, which is a projection on a finite dimensional space, and then argue that in fact this inverse that I can say exists from an abstract point of view is actually a differential operator. So there is a differential operator Q that solves this problem modulo a smoothing operator. Okay, so QP plus that applied to phi equal to phi minus RP. So if phi is in the kernel of P, which is what is of interest to me, then the P phi disappears. I only get this part. Okay, and then I can reshuffle the thing, separate one factor like that, and put the rest like that, and then I get in this way a left inverse for my operator. This is my operator. I got a left inverse for that. This left inverse consists of an operator Q, which is of order minus m, and this operator is of order m minus 1. So the total order of this operator is actually minus 1. So this is a compact operator. Even after it's a compact operator without restriction to the kernel, and even after restriction to the kernel, it's going to be a compact operator. Symmetry comes from the following formula. So everything is invariant. So I start with so this H is the metric, 2 sections, P and T. This is the contraction of the vector field with the invariant measure M. When I integrate this, I get 0 because this is for a differential of something. Okay. When I can write this as Lie derivative, an actual Lie derivative, not this business here, but an actual Lie derivative of a function times the measure or the density. I then apply Leibniz rule. Leibniz rule will act on H, on this, on psi, and on M. But on H and on M, it's equal to 0. So I only get these 2 terms times M. And then when I integrate, I get 0. And so the integral of 1 is the negative of the order, and then the I that I put as a factor here completes the argument that it's symmetric. It's symmetric as an operator on, let's say, infinity or H1 or something like that. And then one has to argue that it has an extent, that the extension that I'm interested in, which is this maximal domain that I'm taking inside this particular Hilbert space, that it is self-adjoint, and for that I use that this is invertible. So I actually have an inverse for this, and that tells me that that a certain extension, which is the actual extension that I'm taking, actually has a null deficiency indices. So the extension is actually the self-adjoint extension. And the last point, I think, is so details are in some paper, which is like 7 years old. what about the finiteness of the spectrum? So the argument here goes like this. So suppose that P is apolyptic on top positive, but there is a sequence of eigenvalues. These are going to be eigenvalues for my operator and sections that are normalized to 1 in the kernel of P. That's what interests me. Suppose that there is a sequence like that tends to infinity. Again, if not right, tends to infinity. Okay. Then I add these things. So I'm assuming that there is an infinite sequence like that. When I add all these sections, I get a distribution such that P applied to the distribution is equal to 0. So this sum converges in the weak sense, because if you pair this, let's say a finite sum of this with a smooth function, what you're doing is you're looking at the Fourier expansion in terms of the eigenfunctions of the operator. So this converges. Converges to the projection of something on something. So this is a distribution, and P is equal to 0. So by the hypothesis, this has no wavefront set on the part of the characteristic variety of P that is contained in tau positive. This is the hypothesis. Okay. On the other hand, if you pick a point in M and a hypersurface that passes through that point, through P0, which is transversal to P, so you have this picture with the color there, then in a neighborhood of the points in P0, you can write, so again, you take a point in the hypersurface, you push it forward, you look at the value of the section, and you pull it back. Okay, so if you have a solution, P sub k, I should forget the index k here, then that solution satisfies this formula. This is just because it satisfies this equation. This is the equation that it satisfies. Then if I take a infinity function that has small support near the point P0 and do the Fourier transform of the product of this times phi, then what I get is, so what's the formula? The formula is the sum of these gadgets. The phi is the sum of these gadgets. When I take the Fourier transform, only the only dependence in T is here and in the cutoff function, which is down here. So what you get is the Fourier transform of the tau in the transversal direction, translated by the factor tau sub k times the value of the section at the point P. And then what I know is that this sum, the absolute value of this sum, tends to 0 rapidly as tau tends to infinity. This is because of the hypolepticity, the microlocal hypolepticity of P. Okay. This is, each of these guys is a gadget like this. It's a bump, because P hat is a bump. Okay, and they have amplitudes that are proportional to the norm of this vector here. If the norms of these vectors don't tend to 0, then it cannot be smooth, so they have to tend to 0. The argument about being hypoelliptic is an argument. So it's hypoelliptic in a neighborhood of a point. It's hypoelliptic on the whole set. So this gives uniformity in some estimates that allow you to say that because this has to decrease rapidly as tau tends to infinity, maybe by passing through a subsequence of the phi sub k, because it doesn't matter what sequence you take as long as it's an infinite sequence, you must have that for large k, the values of these functions have to be small. And now you repeat, so you do this in a neighborhood of P, and then you cover the compact manifold with so hypolepticity implies that this is rapidly decreasing, and then you conclude that P sub k is arbitrarily small near P0 for large k, and then arbitrarily small for large k on M using compactness. And then if it is small, then the norms cannot be equal to 1. So it is not possible to have hypolepticity and at the same time infinitely many positive eigenvalues. The eigenvalues, by the way, they tend to infinity because one can show that there is some sort of there's a kind of bound which is like a Weil estimate for the number of eigenvalues for this kind of thing, which is, yeah. So these eigenvalues, they are in particular eigenvalues of P, but now of P plus of this operator. Where is the operator? They are eigenvalues for this operator. You can see that, I don't know, eigenvalues for that. But so these satisfy Weil estimates, but these are some of the eigenvalues. So you don't know that they're satisfied Weil estimates, but they do. So if you have infinity many, then they have to go to infinity. They have to increase to infinity. So I think this is it. Thank you.
Thank you very much, Gerardo, for a very nice talk. So are there questions or remarks? Well, in the meanwhile, I'd like to ask you this. So there are infinitely many eigenvalues. So is there some information you can get about the spectral zeta function, say, or also the spectral density, and to relate it with some ergodic, well, it's not even ergodic anyway, so, but some properties of the vector field then. And second, if I just asked the two questions, and then, so, because you talked about this kind of Chern classes, so this is a kind of generalization. So, but if I would like to see things for instance, Pontryagin classes, so it's just the same, or?
The Pontryagin classes, the first Pontryagin class that is that has some information is P4. Okay? And in this case, the classes are C1, so there are 2 forms, not 4 forms. Mm-hmm. So you don't, from that you are not going to get anything, at least directly that I can see. Mm-hmm. I have been thinking about how to prove estimates, better estimates about the eigenvalues, because this would be also give some estimates or another point of view about estimates about. You see, since this is related, it's really related to circle bundles and over of holomorphic line bundles over the complex manifolds. This is actually, you know, the sum of the dimensions of so the counting function for the eigenvalues in that case becomes, in this case, becomes the sum of the dimensions of the spaces HM0, the spaces. Okay, I'm going to write something. Let's see. So we have the dimension of the spaces H0Q of the base. This is the complex case of the line bundle, the tensor power m. The dimension of this for m less than some number n. Okay, so this function. These are some people. This is asymptotics from above that people know that are related to Chern classes. Mm-hmm. So there is a bound from above that has a constant, and the constant is related to an integral to the Chern class of the original line bundle. I would like to prove in this case that one also has this kind of thing. And proving it in this case, I don't know, but it could have other implications. Okay, so this I don't know how to do, but I would like to be able to do it. And then once you do that, then you can say better things about, for instance, zeta functions. Mm-hmm. So there is a two-way road. No, I mean, this is from here to here and backwards. No, this is one or the other. I don't know. Mm-hmm. So this is questions.
Thank you very much. So are there further questions? Well, if not, I thank again Gerardo for his very nice talk. And I think, let me see, so we can have, we have a 20 minutes break till 6. Okay?
Yeah. So,
thank you very much.
Thank you very much.